So today's lecture is going to talk about the different types of electrical currents and specifically how they apply in semiconductors. So we're going to talk about what drift current is, and then we'll talk about how to calculate the conductivity of a semiconductor. Before we do that, let's just back up, just briefly cover the main things that we've done so far in this module. We started off this module by saying, we said that solid materials have different band structures, and those band structures result in energy band diagrams, a continuous band of energy states. Okay. The key thing about those energy states is that electrons can move within a band. So if you had a band, that had electrons and it also had available states, then the electrons can move. And if the electrons can move, then you have a conductive material. We got into the band gaps. We talked about electrons and holes, the two different types of charge carriers. We talked about intrinsic and extrinsic semiconductors and what the hole and electron concentrations are in both of those cases. So in order to calculate carrier concentrations, we first talked about the Fermi-Dirac distribution, and then we talked about the density of states, and then we brought those two concepts together and we found some relatively simple relationships for calculating the electron and hole concentration. All right, so we also mentioned that there's something called an intrinsic carrier concentration, which is a concentration when you have no doping, and then there's extrinsic carrier concentrations, which is when you do have doping. Okay, so that brings us to where we are today. So we're going to look at this problem from first principle. So step back to your Circuits 1 class and think about what is electrical current. Electrical current is moving charge. And the way we think about current in a resistor is that you put a voltage source across a resistor, and by Ohm's law, the voltage is equal to the current times the resistance. V equals IR. So this is the resistor here, and this is the current going through the resistor. All right, so the questions we want to answer here. By the way, this type of current, the standard type of electrical current that you've talked about in previous classes, is called drift current. There's another kind of current called diffusion current, which is specific to semiconductors, which you maybe have not learned in your Circuits 1 class. It's a different type of current due to the concentration of carriers. Drift current is due to a voltage or electric field being applied to a resistive material. So the questions we want to answer here is, what is drift current? How does drift current flow through a semiconductor? And then if we want to make a resistor, the first of the basic elements that we make in a semiconductor is a resistor. How do we calculate the resistance of a semiconductor being used as a resistor? All right, so we're going to look at what happens in a semiconductor when you apply a voltage across it. So this rectangular bar here represents a semiconductor, just a block of it, and you're putting a voltage across the material. So the semiconductor behaves as a resistor, you should get some current. But let's look at what's happening inside the semiconductor. So assume that the semiconductor has some length L. And so the first thing we do is when we apply this voltage, it generates an electric field. All right? The electric field is equal to V divided by L. All right, so the units for electric field is volts per meter, but in this class we use volts per centimeter. Okay, so the way that you can think about electric field is that the electric field gives a force. That force causes the charge carriers to move. So the electric field is pointing in from the right to left direction. So it points from the positive end of the voltage source to the negative end of the voltage source. So your electric field is pointing from right to left here. Your conductive material contains charges. We did that in last class. Right? We figured out how to calculate the electron and hole concentrations. Now, for simplicity's sake, this diagram is just showing electrons. All right. Now, the charge density the units for charge density would be given in coulombs per centimeter cubed. Last time in class, we talked about electron concentration. So the units for electron concentration would be electrons per centimeter cubed, or sometimes we say 1 over centimeter cubed. We don't even put the electrons in the numerator. So the difference here is that the charge density is the electron concentration times the charge per electron. And let me just note that down here. This is equal to the electron concentration times Q of the electron. And the Q of the electron, remember, is 1.6 times 10 to the negative 19 coulombs. All right, so a conductive material has something called a charge density. And the units for that charge density is coulombs per centimeter cubed. All right, so you just imagine all these electrons that are in the material. And these are the free electrons, remember. These are not the electrons that are bound in the covalent bonds. These are the loosely bound electrons that are in the lattice. So these electrons can move if you apply voltage to them because they're loosely bound. All right, so you create this electric field, and the electric field applies a force. Okay, and because of that force, the charges begin to move. Which way are the charges going to move in this case? If the electric field is oriented from right to left, which way are the charges going to move?
Right.
In the opposite direction. Right. Negative charges move opposite the electric field, and positive charges move in the same direction as the electric field. Okay? All right, so the way that conductivity is defined and the way that mobility is defined, this is mobility we're talking about here. Mobility is this thing that's a mu that you see here, okay? The velocity of the electrons, the average velocity of the electrons, which is in centimeters per second, is equal to the mobility times the electric field. It's linear with respect to the electric field in the basic model. The way that you can think about this intuitively is that if you apply more electric field, that's going to generate more force on the electrons. Remember that relationship, F equals EQ? So the more electric field you have, the more force you have, and the faster you're pushing the electrons. So it kind of makes sense that the velocity of the electrons will be proportional to the electric field that's applied. All right, the proportionality constant is this mobility mu. And what we're going to find out is that mobility actually has a lot to do with the material properties. It has to do with something called scattering in the material, and the electrons bumping around as they move. All right. So the way that you can think about this is the electrons are moving through the lattice. Sometimes they bump and they move, and the bumping changes their trajectory. But overall, they're moving in the direction opposite the electric field. We'll talk more about that bumping or scattering effect later. All right. Next is that's the velocity of the electrons. So the average velocity is going opposite the electric field. When you have a set of moving charges, it creates something called a current density. Moving charges is electrical current. But let's define specifically what current density is and what the formula for that is. There's quite a simple formula here. The current density is equal to the charge density, which we defined up here. The charge density times the velocity. If you think about this in terms of units, charge density is, the units for charge density is coulombs per centimeter cubed, and the units for velocity is centimeters per second. All right, so you have coulombs per centimeter cubed for charge density, and the velocity is centimeters per second. All right, so what do you get when you multiply those two together? So you're multiplying coulombs per centimeter cubed times centimeters per second. Was it? Sure, we can do it here. QV, so the units for Q is coulombs per centimeter cubed, and you're multiplying them by centimeters per second. So what do we get here?
Coulombs squared per second.
Yeah, coulombs per centimeter squared per second. All right. Now, this part here, coulombs per second. What's coulombs per second? That's current. Remember, current is coulombs per second. That 1 amp is 1 coulomb per second. So this part here is an amp, And so the units that you're left with is amps per centimeter squared. That's what you see here. And the way that you can kind of think about current, when we say coulombs per second, what are we actually talking about? If you imagine if you imagine a cross-sectional area A, all right? So think of this as a finish line, okay? And there's a judge sitting at the finish line, and that judge is basically counting how many electrons pass by the finish line per second, right? That's the way to one way to think about current. If you imagine those electrons as cars and the number of cars passing by that point per second, passing through that cross-sectional area. So coulombs per second, the number of the amount of charge that passed by that cross-sectional area per second, that is the current. All right. So the current density is the total number of electrons that's passing through this cross-sectional area divided by the area. Okay, so let's say 10 electrons pass through this shaded region per second, and then the area is 2 square centimeters. Then it would be 10 times q divided by 2 square centimeters. Right. So current density is the current divided by the cross-sectional area. So the current is basically the cross-section, the current density times the cross-sectional area. All right, I kind of explained it in the backwards direction. I first defined current, and then I told you what current density is in terms of current, but you can think about it the other way around too. It's current density. So the current density is obtained by multiplying the charge density times the velocity. So it's Q times the mobility times the electric field there. And then if you want to find the total current, then it's I equals J times A. It's the cross-sectional area of the block. Right, so the larger the cross-sectional area, the more ability a wire has or a material has to pass current through, pass charges through, right? So that's one of the reasons why large diameter wires are used to carry large amounts of current, like in power distribution, for example. All right, so all the units here are given so that you can, if you want to look at this later, voltage is in volts, electric field is volts per centimeter, the length of the resistor is centimeters, the velocity centimeters per second. Mobility, the units for mobility is centimeters squared per volt second. Okay, that's a good one to remember. Current density is amps per centimeter squared. Charge density should be coulombs per centimeter cubed. There's a typo here. Coulombs per centimeter cubed. Current is 1 amp, which is 1 coulomb per second. And the cross-sectional area is given in centimeters squared. Okay? So any questions about drift current here? Voltage creates electric field pushes charge carriers in a material. Those charge carriers move at a certain velocity, and when they move at a certain velocity, that's basically a current. And this is how you calculate the current we just went over. All right, so now in semiconductors, keep in mind that there are also holes in addition to electrons. So we would do the same analysis for holes as well. And the two effects actually superimpose on each other. So you can calculate what the holes are doing, and you can calculate what the electrons are doing separately, and basically sum up the currents due to a whole electron, sum up with the current due to holes, and then you'll get the total current. So this is a discussion question. So let's say we have a voltage V across a material. Then we get some sort of current, and then we double the voltage to 2 volts. So which of the following occurs? The velocity of the electrons double, the velocity of the electron doubles and changes direction, velocity of electrons stays the same. The velocity of the electron stays the same but changes direction, and then the electric field gets cut by 50%. Let's start with each one of these. Let's just go through each one at a time. Is the first one true? The velocity of the electrons double. If you double the voltage, does the velocity of the electrons double?
Yes.
Yes, because the velocity is proportional to the electric field. V is equal to mu times E. If you double the electric field, you double the velocity. Next question. The velocity of the electrons doubles and changes direction. Is that true? No. What would cause the electrons to change? What would cause a change in direction?
Changing polarity.
If you change the polarity of the voltage, right? And if you have holes instead of electrons. Holes would go in the opposite direction of the electrons. The velocity of the electron stays the same, nothing changes. No, that's obviously not true. The velocity of the electron stays the same but changes direction. Also not true. We established that it doesn't change directions. The electric field gets cut by 50%. No. What happens to the electric field?
Doubles.
It doubles. Correct. Okay, good. So we're all on the same page there. Let me add another question here. So if we double the voltage, what happens to the current?
If the resistance is constant, it doubles. It will be doubled as well.
It doubles, right? The current doubles. What happens to the current density?
Double.
It's
It will be the same.
Nope.
It will be double because
the current density doubles also. All right, because the current density is
charge mobility is half, right?
yeah. So what happens? You double the voltage. So by doubling the voltage, you double the velocity. If you double the velocity, you double the current density, and then you also double the current. All right. So another example here. This is one for the homework. If we have time at the end of the class, we might come back to this. But I think this is one that you just want to do as homework. It will take some time to do this. Actually, not too much. We'll come back to it if we have time. But this is a simple example where you calculate the velocity of the holes and electrons based on a voltage that you put across here. So I would suggest doing this problem just as on your own, as a homework problem. So let's see. Now, getting to electrical resistance. So we figured out physically what's happening. We figured out that these charge carriers are moving at an average velocity. We figured out the current and the current density. So now we can then figure out the electrical resistance. So the resistance, the way that it's defined by Ohm's law, is just the ratio of V over I. So but just by plugging in some of the formulas that we saw earlier, we can come up with the formula for the resistance. All right, so let's look at this. The electric field is equal to the voltage divided by the length. That's what we defined last time. We also defined the current density as Q times V, and the current as J times A, the current density times the cross-sectional area. So the current is equal to Q, the charge density, times the mobility, times the electric field, times A. All right, so we have relationships that relate the voltage, the current, according to the material properties. So if you just take the ratio, of V over I, all right, so the relationship for V from here is V is equal to the electric field times the length. So that's what you get this on the numerator here. And the current is equal to Q times mu times E times A. So you have this on the denominator. And notice that the electric field is in the top and the bottom. Okay, so those two cancel, and you're left with L divided by charge density times the mobility times the cross-sectional area. So from here, now we're going to separate out two things. This one, if you look at the L, which one of these are material parameters and which ones are geometric parameters?
L is geometric.
L and A are geometric parameters, right? And Q and mu,
Material.
that has to do with the material properties. So as engineers, we like to separate those two out because the material properties, the Q and the mu, are going to be determined by how the material was made. So what would it depend on? How can you control mu and Q?
Doping.
Doping, correct. The mobility also depends on doping and temperature, both. And then the geometry is controlled by layout. So when designers actually design a, let's say a mixed signal circuit that has resistors in it, what they'll do is they'll say, like, I want to create a p-type semiconductor, and I want the depth of the p-type semiconductor to be this much. Actually, the depth is controlled by the process, but the width and the length I can control by doing my CAD design. I can actually draw how long I want the resistor to be and how wide I want it to be. So the process engineer is the one that is determining the material properties, Q and mu. The design engineer, like the VLSI, the CAD engineer, is the one who's determining L and A. Right? The VLSI engineers, have any of you taken a course in VLSI? You have, David? So you remember how you, in Cadence, how you lay out
Yeah, it's a lot of stuff.
lay out the lengths and widths of all the transistors?
Yeah.
So that's essentially, this L and the A are coming from that. So you control the VLSI engineer controls the dimensions, and the process engineer controls these two. So so the conductivity, they take Q and mu and they put that into a conductivity, so a material property, and the L over A they leave separate because that has to do with the geometry of the material, or the geometry of the resistor. Sorry. So this sigma here, this is the conductivity of the material, and recall that Q is the density of charge carriers and mu is the mobility. So this is a formula for mu. Sigma is equal to Q times mu. This is only if you have a single carrier. Okay, later in the chapter, later in the module, we're going to look at if you have both electrons and holes. So you actually have to sum up both contributions. It'll be Q times mu n plus Q times mu p, where the mu n is the mobility of the holes, and then mu p is the mobility of the mu p is the mobility of holes, and mu n is the mobility of the electrons. All right. Any questions on resistance so far? All right. This is a quick problem, so we can do this really easily. Let's just do this. Suppose the conductivity of a semiconductor is 2 ohms per centimeter to the -1. What is the resistance of a bar of this material? The length is 1 centimeter and the cross-sectional area is 0.1 by 0.1. So this is quite a straightforward problem. So if you imagine we have our bar that looks like this, and we're applying the voltage between the ends of the bar, the resistance is equal to L divided by sigma times A. The length is 1 centimeter. The conductivity is 2 ohm centimeters to the -1. And then the area is 0.1 times 0.1 centimeters squared. All right, so the units for mobility is ohms, centimeters, and so the centimeters, you end up getting centimeters squared on the top, and it cancels with centimeters squared on the bottom. So you're left with just ohms as the units. So it's 1 over 2 times 0.1 times 0.1. So it's 1 over 0.02. Sound right? So this is 50 ohms. Okay. Pretty straightforward problem there. So, if we double the cross-sectional area of a material, what happens to the resistance? This discussion question. If we double the cross-sectional area of the resistance, that's right, it gets cut by half. Right, good. What if we double the conductivity?
Same thing.
Same thing, right. What if we, no, you're correct. You guys are correct. What if we double the length but half the width? No, I'm sorry, what if we double the length and we double the width?
Nothing.
Nothing happens, that's right. If we double the length and we half the width?
4 times increase.
Yeah, there you go. So the cross-sectional area, just to remember, the cross-sectional area is this dimension, which is the width, by this dimension, which is the thickness, and then this is the length here. The length is the axis on which the voltage is being applied. So the length is the direction, is going in the direction in which the electrons are moving. Typically, the width of a material is something that the CAD designer can control. I think that must be my phone. I think I just need to wait until it goes away, sorry. The width is something that the CAD designer can control. The thickness is also something that is part of, it's within the control of the, actually the thickness is actually within the control of the semiconductor engineer also. The length and the width is what's drawn in the CAD model. The thickness is determined by the semiconductor process. When you do a diffusion process, typically what a semiconductor resistor would look like, let's say you have an N-type material, you create a diffusion zone here, and then you have like your 2 contacts up here. So the current goes through the P-type material, for example, and it goes out this way. It doesn't leak out into the N-type material because there's a P-N junction there. That's beyond the scope of this discussion. But to create this P-type resistor, you're going to diffuse in P-type dopants to change this material from N-type to P-type just in this zone. And the amount of time you spend in the diffusion furnace determines the thickness T here. All right, that's why I said the T is sometimes under the process engineer's control. The length and the width are done by the CAD engineer. Yeah, David.
So most components today are surface mount, so at least basic ones.
Mm-hmm.
So wouldn't the standard footprints more so dictate the envelope than?
Oh, you're talking about like chip resistors?
Yeah.
Yeah. So, well, chip resistors are kind of they're made from a wide variety of materials. They're made from metal films. Sometimes they're made from semiconductors. Sometimes they're made from high or low conductivity things. They're not always like. In fact, like the basic resistors, most of the times they aren't semiconductors. They're just made from like alumina or metal films, things like that.
Okay.
Like bulk materials.
So this is just like really small transistor level.
Yeah. So if you want to make an integrated circuit on a chip, integrated in silicon, so you have like your transistors, and then you also have your resistors on there, like everything integrated. This is how you would lay that out.
Okay.
Yeah.
Okay.
Okay, now that we've talked about what electric fields and velocities are, let's talk about scattering. I mentioned in this discussion, in this discussion I mentioned that when you apply this electric field, the electrons start moving in this direction, but remember the electrons are always bumping into things. What are they bumping into?
Electrons.
They could bump into other electrons, yeah. They could also bump in, what else?
Balls.
Air molecule?
I guess air molecules would be possible. This isn't a solid material. The air molecules, there'll be fewer of those unless they've diffused in. But I think generally you can assume that there's no air molecules. This is a semiconductor material. So in the material, what is there? There's electrons, and then there's
The lattice.
the lattice, right? The lattice consists of there's nuclei, right? The nuclei, and then there's the electron clouds around the nuclei, right? So the electron clouds have an effective negative charge, and the nuclei have an effective positive charge. So if you forget about Schrodinger wave mechanics for a second, you just think about these things as particles, they will get impacted. They will be their directions could change if it's going towards a nucleus, right? If it goes into an electron cloud, then those electrons would cause it to deflect, and the electrons could deflect off in a different direction. Conversely, if you see a positive charge, that will cause the electron to deflect towards it. So there can also be collisions. The electron can actually bump into something and then bounce off like a billiard ball. Okay. When we think of particle-like behavior, that's one that's one way we can think about scattering. Right. Compare this to free space. In free space, in vacuum, the electron just goes. There's nothing that it bumps into. There's nothing that causes it to deflect in one direction or another. Right. So what's gonna happen if we were to compare the situation where we have a vacuum? We put an electric field across a vacuum and we let an electron accelerate. Versus if we do the same thing in a semiconductor material. Which case do you think the electron is going to move faster?
Vacuum.
In vacuum. There's less collisions, right? So which material has a higher mobility? Vacuum. Right. Exactly. And vacuum actually doesn't have a mobility. All right. Just to be very specific. Vacuum you can think about as having infinite mobility. There's no bumping around. There's nothing to slow the electron down. So the electron just continues to accelerate until it gets to the end of your, it accelerates to whatever potential you applied to it. Remember how we talked about classical mechanics? We said that the electrostatic potential energy is converted to kinetic energy. So that electron will accelerate, and the velocity it'll have at the end is whatever the potential energy was. Versus, in the case of a semiconductor, if you put a voltage across there, you have this potential energies, and that potential energies be converted to kinetic energy, so the electrons start to move, but the electrons are also bumping into things. Right? It does a scattering. So the electrons don't actually, the potential energy is not completely converted into kinetic energy.
So could the electrons collide with just the free electrons in the semiconductor, or they may go to inside the lattice and go from the final orbit to the next orbit to a lower energy?
They can, when they scatter, they can go to lower energy states. We'll talk about that later in this module and in next module. So there's ways that we can, one way we can think about it, in terms of the particle behavior. We can think about the electrons as bumping into things, right? And when it bumps into things, it changes direction, right? So that slows down the velocity. That means that potential energy is not being completely converted into kinetic energy. We also know that when things bump into each other, it generates heat, right? So that's the particle-like behavior. The way you can think about it is scattering in terms of the particle-like behavior. Now, the way you can think about it in terms of energy band diagrams is that an electron, when it bumps into things, when it scatters, it can potentially, that's one way that it loses energy. So if an electron is in a high energy state, a high energy state meaning it has a lot of kinetic energy, there's a lot of potential energy and that's causing the electron to accelerate. So that represents a high energy electron, high momentum, and that when it collides, it loses some of that energy, so it goes into a lower energy state. Does that sort of make sense? We're going to talk about energy and momentum later in this chapter. I don't know if we'll get to it today, but next class we'll probably get to that, and then it'll hopefully make more sense. So if there's let's talk about what's on this slide here. Okay, in a solid material, electrons collide with lattice vibrations. That's called lattice scattering, or lattice impurities. That's called impurity scattering. We'll have one slide on each one of those, so I'll talk about each one of those in turn. But what is scattering? It's when electrons like collide or deflect. So if you imagine that there's no electric field, okay, so you just have the semiconductor material sitting there. The electrons still actually move. They move in a random fashion. Okay, at any non-zero temperature. If you're at absolute zero, then the electron movements stop. But if you're at non-zero temperatures, like room temperature, the electrons are moving around, but they're moving in random directions. So over time, the net displacement of the electron is zero. Right? Because it moves in this direction, then it moves in the other direction, then it moves in the other direction. So it's what's called a random walk. And so the average velocity is zero, and so there's no current. But if you have an electric field, I mentioned that the velocity is opposite the electric field. So if the electric field is pointing from right to left, then the electron moves from left to right. So if you imagine that the electron starts moving in this direction, then it collides with the nuclei, or it's deflected by a nuclei, or it's deflected by an electron cloud, and that causes it to change direction. So it starts, it turns 90 degrees here, but then the electric field causes it to again go forward in this direction. It scatters here again. It initially starts going off in the upwards direction, but the electric field pulls it back, and then it starts going here again. So over time, it eventually goes at the average velocity is opposite the electric field. So it has a net or average velocity. Okay, even though these scattering events are slowing down the effective speed. All right, so any material where there's less scattering is going to have a higher mobility. This scattering is what determines that mobility parameter that we talked about on the previous slide. Less scattering, higher mobility. More scattering, you reduce the mobility. And we talked about graphene, the first module. That's one of the materials that there's a lot of interest in. One of the reasons for that interest is the high mobility. Because of the two-dimensional structure of graphene, the electrons can move through that structure with fewer scattering events. And that's the reason why materials like graphene have high mobility. Carbon nanotubes also have high mobility. Okay, so it's a bit of a busy slide, but this defines what mobility is. The mobility is a constant which describes the ease with which the electron or hole can move through the material. I mentioned higher mobility means the electron is moving faster through the lattice, fewer collisions. Conversely, if you have more collisions, the mobility will be lower. So we can think of the electron as a particle with effective mass. I'll talk about effective mass later, so just don't worry about that too much right now. The way that you can think about this in terms of mobility is that it's intuitive to think about mobility as being inversely proportional to effective mass. So meaning that like if a particle that has smaller effective mass can move more easily through the material. Going back to if you look at that drawing that we had in the previous slide, the electron think about it as a particle, it's bumping into things, right? So every time it bumps into something, it could change direction. And the electric field has to pull it back into the correct direction. Does that make sense? Right. Now, what's going to be easier, like if you have a big heavy particle or if you have a super light particle? Yeah, right. If we're thinking about this thing in terms of particles, like the particle-like behavior, a particle has mass, a particle has momentum, a particle has inertia, right? A heavy particle, the electric field, remember, is exerting a constant force on that particle. Force is equal to E times Q, which Q is the charge of the particle. So the force is constant. If you have a heavy particle, then it's gonna accelerate slowly. Versus if you have a light particle, it's gonna accelerate rapidly. All right? That's what we're talking about, effective mass. So this statement I made where it said like a particle with smaller mass can more easily move through the material. Because when the particle's moving through the material, it collides, changes direction, but then the electric field accelerates it back in the direction that it's supposed to go. Something that has low mass, low momentum will be easier to accelerate whenever it collides. Right? It has less mass, so it's easier to accelerate it.
And that's because when it collides with something, usually it goes goes with the electric field. It wouldn't collide and then keep moving forward.
No. Usually a scattering event causes some kind of deflection.
Okay.
It's not always exactly in the opposite direction. It could just be like it curves off, but it causes the change in direction. And the electric field has to pull it back in the correct direction. It has to accelerate it back. Force is equal to ma, right? So if you have a large mass and you have the same force, then the acceleration is slower. Right. Okay, so the mobility is equal to, it's inversely proportional to the effective mass. Lower mass equates to a higher mobility. The thing on the top, it says the mean time between collisions, and then the Q is the charge. So this also should make sense, because if you think about it, like the more frequently that the electron collides, what's going to happen to the mean time between collisions? If collisions are happening very frequently,
Gonna go down.
the mean time between collisions is lower, right? And if T is lower, then the mobility is also lower. Okay. All right. So, we didn't derive this equation from first principles, but this equation comes from statistical mechanics. Right? So what this equation basically is doing is trying to take, we don't care, we're not trying to count up every single scattering event that the electron does, right? We only care about the average velocity of the electron. So statistical mechanics, it looks at how frequently a certain event is happening, like the collisions, and it averages that stuff out into a parameter or a constant that we can use, which reflects the average velocity. So that mobility is the average velocity that we're talking about. Okay, we're going to use mobility a lot in this class. We're not going to use mean time between collisions. We'll talk a little bit about effective mass. So this is the constant that we use. I just want you to understand intuitively where that mobility constant comes from. A material that has few collisions will have a high mobility. When the electron has a low effective mass, it will have a high mobility. The effective mass is actually a more complicated topic, but I said we'll talk about it at the end of this module. All right. This is again showing schematically what's happening when the electron's moving through the material. It says a derivation of mobility. I guess this is a basic derivation of mobility. How about that? Okay. As I said before, the full derivation of mobility, we have to look at statistical mechanics and things like that. But this is a very intuitive way of deriving mobility. So each collision is going to reduce the momentum by delta P. So what we think about this is that the electron, suppose we have an electron and then it's bumping into a silicon atom, meaning this might be like a, either an electron cloud, or it could be some other thing that the electron bumps into, okay? So the electron bumps into that, it changes the momentum. So the change in momentum is equal to the mass times the change in velocity, because P equals mv, momentum equals mass times velocity. So the change in momentum, delta P, is equal to the mass times the change in velocity. All right, so that's what happens in one collision. The fundamental concept here is that the force is the rate of change of momentum. This, if you haven't seen this before, this force is equal to dP times dt. If you think about this in terms of units, this does work out. 1 Newton is equal to the mass times velocity, which is kilograms times meters divided by seconds. Okay, so the units do work out there. It's a change in momentum over change in time. Now, in the case of the electron, the momentum change per unit time is the momentum change per collision times the number of collisions per second. All right, so every collision is changing the momentum by a certain amount, and then how frequently you have your collisions is how frequently those collisions are happening. You multiply those two together, and you get the net change in momentum over time.
Is this essentially the same way that gel electrophoresis works?
Is it the same way that gel electrophoresis works? So gel electrophoresis, you put an electric field over the gel, and the molecules are translocating through the gel, and they move through the gel with a certain mobility. So yeah, the concept of mobility is actually the same. The difference is in a gel, it's not actually collisions. It's actually the molecular sieving action of the pores of the gel. Small pores make it harder for stuff to move through. Larger pores, stuff can move through more easily. But it still gives you an effective mobility. That's what I'm saying. The cool thing with this stuff is some of these things is that it gives you a bulk property, the mobility, and then once you have the mobility, then all the other relationships that I showed you earlier, where velocity is equal to mobility times electric field, that holds. This is just a way, where's the mobility coming from in the case of an electron moving through a lattice, where the electrons keeps on colliding with things. All right, so dP dt is mv mv divided by t. All right, now you think about the scattering force that slows down a moving electron, and that scattering force opposes the electric force. And so if you set the two forces equal to each other, you solve for the velocity. So this force that we just derived, quote unquote, the scattering force is equal to the change in momentum divided by the change in time. Now what that is an average force exerted by all the collisions. The electron is trying to move in this direction. So the electric field is applying a force. Force is equal to E times Q, making the electron want to move opposite the electric field. The electron keeps on bumping into things that slows the electron down. So those collisions can be represented by a net force that's slowing down the electrons. Okay. The best analogy here is drag. If you imagine a car driving down, hurtling down I-75 because you're late for this class, right? So the faster, what happens to the drag force as you increase, as you put the pedal to the metal? Huh? The drag force increases, right? The drag force is proportional to velocity. Okay? If you're going at twice the velocity, you're actually going to have twice the drag force because the air molecules are slamming into your car at twice the speed. So that's what drag is. You think about the electrons like moving through this lattice. The collisions cause something on the order of a drag force. So you have the scattering forces like the drag force, and that's slowing the electron down, and then you have the electric force, which is causing it to move in the forward direction. If you set the scattering force and the electric force equal to each other, so the scattering force was mv divided by t, and then the electric force is q times e, and then you come up with this mobility equation. Velocity is equal to qt divided by m times the electric field. T is the mean time between collisions. Q is the charge of the electron, and then m is the mass of the electron, the effective mass of the electron. Okay, so questions about mobility? These types of mobility can actually be applied, as I mentioned, to many other fields of things. When you're talking about the movement of gas molecules, movement of whatever, they all derive from statistical mechanics. All right. So I want to just briefly talk about the two types of scattering there are, like the two mechanisms. The first type is lattice scattering. So in any solid material, the atomic lattice vibrates at temperatures above 0 Kelvin. You go to 0 Kelvin, the vibrations basically go to 0, and that's why a lot of scientists or physicists, they do experiments at 0 Kelvin, because these lattice, if you eliminate a lot of these lattice vibrations, it changes the mobility, and all your instruments, because they have fewer vibrations, molecular vibrations, you can take measurements with a lot less noise. Okay, so but at non-zero temperatures, the silicon atoms are vibrating. Okay, the nuclei are vibrating, the electron clouds are sort of vibrating. They're called thermal vibrations, and lattice scattering is when an electron collides with this vibrating lattice, causing it to change direction. Okay, so because this scattering has to do with the vibrations, the scattering rate is proportional to temperature. And we're not going to go into the details of why, but it's actually proportional to the temperature to the 3/2, not just proportional to temperature to the first power. So more thermal vibrations results in more thermal vibrations at higher temperatures results in more lattice scattering, and it would reduce the mobility of the electron. More scattering reduces the mobility. The second type of scattering is called impurity scattering, and this is scattering deflections caused by ionized donors. And the way you can think about it is quite simple. Suppose you have a silicon lattice like this, and you have your arsenic. Does anyone remember why is the arsenic? Why does it have a plus associated with it? Why is it an ion?
Yeah.
Was it? Well, arsenic is this is an N-type silicon. So arsenic is a column 5 element.
It donated an electron to the lattice.
It donated an electron to the lattice. That's right. And that electron went away.
So now it has one more proton.
So now it has one additional proton there. That's why the nucleus has an effective positive 1 charge compared to the other atoms around it. Well, actually, just on its own, it just has a positive 1 charge because it had an extra electron in there, an extra proton, and but then electron went away, so it leaves a positive charge. So this electron, imagine an electron moving like a particle, moving at a very rapid velocity, and so the electric field, let's say the electric field is moving from right to left, so that causes the electron makes the electron want to move straight like this, but the electron is also impacted by Coulombic attraction to this ion, so then it just gets deflected like this. Right? This is also what they do in, when they take the satellites to space, and sometimes they actually deflect it off planets. They use the planet's gravitational field to send off the spacecraft in a different direction. It's really cool how they do this. It's pretty awesome. Like I was watching this thing on the Voyager spacecraft. It's on Netflix. It's about the history of the Voyager spacecraft. They did this stuff a lot where the Voyager was, they sent the Voyager spacecraft towards one planet, and they used the gravitational field to accelerate it and change the direction and send it off in a different direction. So the point is that, you might think that why isn't the electron just like going and just going right into the nucleus? Like why isn't it crashing right into the nucleus? Well, first of all, it wouldn't do that even if it had no velocity, because there's all these electron cloud functions around it too that impact the forces as well. There's electron clouds around the nucleus that affects where it's attracted to and where it's not. And secondly, is that you also have a velocity here that's causing the electron to move in a certain direction. So the faster this electron is moving from left to right, the less likely it is to just go, the less likely the trajectory is to go right into the nucleus. Does that make sense? It's like with the satellites. If you send a satellite hurtling towards a planet at relatively low velocity, then the planet's gravitational field will suck the satellite in and it'll just crash. But if you toss it if you hurtle that satellite towards a planet at high velocity and at the right angle, it'll be affected by the planet's gravitational field, and it'll be deflected off in a certain direction, but it won't crash into the planet. Anyway, that's an aside. Interesting stuff. But impurity scattering, you can imagine that this is due to this Coulombic attraction between the electron and the positive ions at a very basic level. At a more complex level, you have to think about, if you think about it in terms of wave functions, you have to think about how the wave functions overlap and how that changes the electron probabilities. But I would say just think about this in terms of in the particle mindset. So obviously, the more impurities you have, the more the impurity scattering is going to become significant. So if you have more dopants, if you increase the doping concentration, what's going to happen to the mobility of the material? Mobility will decrease at high doping densities. Correct. All right. So there's also a temperature dependence of impurity scattering as well. At low temperatures, there's less thermal vibrations, the electrons move slower, so they spend more time near the dopant ion. This results in more deflection. So if the electron is moving slow, this is a satellite analogy I was telling you about. If the satellite's moving really slow, it'll get more deflected by the planet by planet's gravitational field. If the satellite's moving very fast, it gets less deflected. So there is a temperature dependence here with the electrons as well. The electrons move slower at lower temperatures. This becomes more of a significant scattering. There's more of a deflection in the trajectory. At higher temperatures, the opposite occurs. Okay, so impurity scattering has both the doping and temperature dependence. All right, discussion question. Which of the following is not true? Lattice scattering depends on the vibrations in the atom. Let's just go through one of these at a time. So lattice scattering depends on the vibrations in the atom. True or false?
True.
True. Second question. Mobility is proportional to the number of collisions per second.
True.
It's inversely proportional.
It's inversely proportional to the number of collisions per second. So the mobility is proportional to the time between collisions. When the time between collisions is large, the mobility is also large. So that one is not true. Collisions slow down an electron. True. If mobility increases, we can expect the velocity of the electron to also increase. True. A smaller effective mass will increase mobility. True. Good. Right on. All right, more questions on mobility. So this is a chart of mobility, the dependence on doping. We just talked about this a little earlier, but let's look specifically at silicon. That's the material we mostly look at in this class. So this is mobility versus doping at room temperature. So you notice that this is the mobility of the electrons and then the mobility of holes. So one of the things I want to point out is that holes have a higher effective mass than electrons do, and because of that, they tend to have a lower mobility. In most cases, they will have a lower mobility than electrons. They have a higher effective mass. But the main point of this graph is to show you that as mobility increases, as doping concentration increases, mobility decreases. It's fairly flat on this part here. So when you're below 10 to the 15th or so, there's really no effective doping and mobility. This line just goes straight out, and that's why these charts don't even bother showing it. But once you get above 10 to the 15th, 10 to the 16th, then the mobility drops fairly significantly, because this is a log scale. So by the time you've increased doping to 10 to the 19th, your mobility has dropped by a factor of 10 due to impurity scattering. The same thing holds true in these other materials as well. All right. So if you compare these materials also, it's interesting to see what the mobilities are. The silicon has mobilities in the 10 to the third range. Germanium has slightly higher mobilities. It's closer to 10 to the fourth, or 1, 2, 4. Like it's about double that of silicon, and then gallium arsenide is also quite high here. And then gallium arsenide has a large difference in electron and hole mobility. All right. So whenever you have high mobility materials, those materials are often useful in high-speed semiconductors. High-speed semiconductors are the ones you want the electrons to move through the material very rapidly. High mobility results in lower resistances. So if you want to think about you can think about circuits as electrons moving through the circuit at a certain velocity. You can also think about it in terms the way the circuit designers think about it is that you have a resistor. You have resistances and capacitances. So if you have a high mobility material, you're going to have lower resistances everywhere in your semiconductor, right? Because high mobility means low resistance. So if your resistances are lower, your RC time constants are going to be smaller. Right? You think about like an RC filter, resistor and a capacitor. So smaller resistances results in smaller time constants, and so you get faster switching. All right, so some questions. Why does mobility decrease with increasing impurity scattering, impurity concentration? I think we answered this already. It's more impurity scattering. Why is the mobility of holes lower than electrons? We answered that already too. Yeah, they have a larger effective mass. That's right. Cool. It is worth it, to go through a couple of these. Holes have a larger effective mass. That is true, right? Holes move more quickly through the lattice.
No.
That's false, right? It has lower mobility, so it moves more slowly through the lattice. Holes collide less frequently. Fewer collisions. It's determined by both effective mass and the number of collisions. So this is a bit of a murky answer there. It is not known. Holes are positively charged. That's not the reason why the mobility is lower. All right, let's do the temperature dependence of mobility. This is what the temperature dependence of mobility looks like. Temperature is on the x-axis, it's on a log scale, and the mobility is on the y-axis. So what you notice here is that there's a temperature at which you get the maximum mobility. All right, and this happens to be the temperature that we often operate silicon. And all of our computer chips are typically would operate at, at this type of temperature. Now, when you go to higher temperatures, the lattice scattering effects, which cause a decrease in mobility as a function of temperature to the -3/2. So the mobility goes down like this. And when at lower temperatures, the impurity scattering causes the mobility to go down like this as well. So there is a sweet spot where you'll get the highest mobilities for your semiconductor device. So the way that this has implications in the real world is that suppose Intel makes a microprocessor, right? And the microprocessor they give you a spec that this microprocessor only operates in this temperature range. If you try to overclock the processor, you know how sometimes gamers or people who are doing like very intensive computing, they'll try to overclock the processors. And if you don't cool it properly, then the temperature will go up. If the temperature goes up, there's more scattering and the mobility goes down. All right, so how do you think that's going to affect the speed of a processor? It's going to slow it down because it's going to create larger resistances, larger RC time constants. Right. Now the electrons are just going to move more slowly through the material. So that's the reason why cooling semiconductors is very important nowadays. I don't know if you've ever seen...
Instead of using fans, can you use liquid, some kind of liquid?
Oh yeah. Here, let's look at liquid cooling of semiconductors. Gaming. Yeah, if you look at some of this stuff, I don't know if we can find a picture of it. Let's do an image search real quick. Oh yeah, this is cool. Look at that. I've actually seen some of these things. It's for people who really love gaming. They're they have these liquids like passing over their microprocessor, and it's like a refrigerated liquid that keeps it cool. Another example is, I don't know if you've ever seen a picture of Google data centers. Let me see. If not, you can certainly you can read about this. Yeah, look at this. This is cool. I love this picture. Let's go back to that image. Yeah, this is a picture of like what one of their data centers looks like, and you can see that there's more cooling pipes than there are computers. The microprocessors are only taking up a small portion of the data center. Most of it is this stuff, the cooling. All right. So it all comes down to the scattering, the lattice scattering, right? If you don't keep the temperature operating at the right, if you don't keep the semiconductor operating at the right temperature, you're going to increase your resistances a lot, and that's going to mess everything up. You designed your circuit to operate, when you laid out your transistors on your chip, you said, okay, this is going to have this resistance, this one's going to have this resistance. If all of a sudden all your resistances in your 1 billion transistor system doubles or triples, then you're done.
So then, you're talking about cooling down like room temperature, but do they actually try and cool to lower temperatures to try and increase the...
Yeah, you can certainly try to cool it even further, but if you're operating at the sweet spot here, then you don't need to cool it further. In fact, cooling it a lot could actually hurt you, because you want to be kind of at the sweet spot. It turns out this is an interesting fact that cooling the semiconductors costs an enormous amount of energy. We always talk about nowadays, if you hear about this in the news, that data centers consume massive amounts of energy. One of the massive causes of the energy in the data centers is the cooling systems for those. And the other cause is, of course, the chips themselves. One of the reasons why cooling has become a particularly nasty problem in the last 20 years or so, 10 to 20 years, is that, remember, with Moore's law, we were making our transistors smaller and smaller and smaller, right? So we're packing more and more transistors into a small area. And each transistor generates a certain amount of energy, or lets off a certain amount of heat every time it switches from high to low. So when you pack all those transistors together, it's just like if you pack a bunch of people together. Like each person is also generating heat, right? So if you pack a bunch of people together, and the temperature goes up. You pack a bunch of transistors together, also the temperature starts to go up. So it becomes tough to keep these chips operating at a good temperature. Overheating is a big issue. One of the things that some of you may have noticed, maybe you've noticed it. Have you noticed that when your laptop gets really hot, sometimes it operates more slowly? Well, one of the things that some manufacturers started to do, it's just very clever. It took a lot of engineering, but what they did is they said, like, okay, we know that at higher temperatures, all of our resistances in the system is going to go up by a certain amount. If all the resistances go up, then our time constants are also going to increase by a certain amount. And so our chip is essentially slowed down. So what they do, in order to keep the chip working at the higher temperatures, they just slow down the clock rate. So if your entire microprocessor is operating more slowly, it can't operate at 3 gigahertz, they'll just take down the clock speed to 1 or 2 gigahertz. So your system won't die, it'll just operate more slowly. Conversely, as I mentioned earlier, the gamers who are overclocking, they're trying to get them up to like, close to 4 gigahertz. They're the ones who are using like active cooling techniques to make sure that that the temperature doesn't get too high. All right, so here's a mobility of some popular semiconductors. As you'll see, the whole mobility is often less than the electron mobility, as we just talked about. This is a chart of three-dimensional traditional 3D materials like silicon, germanium, gallium arsenide, indium arsenide, indium phosphide, and so forth. And one of the things you'll notice here is that the indium materials have massive electron mobilities, right? Almost like tenfold higher than silicon, sometimes even more. Germanium has more than twice the mobility of silicon. So high mobility materials are useful for high-speed electronics. Gallium arsenide has 8,500 mobility. Gallium arsenide was widely used in high-speed amplifiers. So things like military applications, military radar that operate in the many gigahertz range. So high mobility materials have less resistance, lower transit times, both of which are useful in high-speed digital and analog circuits. There's also, I mentioned briefly, that emerging 2D materials. This is from Module 0, where we talked about some emerging trends in semiconductors. But this plot shows you electron mobility on the y-axis and then band gap on the x-axis, the two most important properties for an electronic material. Now that we've covered some of this stuff, now this chart should hopefully make a little bit more sense, is if you're an engineer and you're trying to decide, well, what material should I use for my specific application? You're going to obviously consider cost, and you're going to consider mobility, and you're consider the band gap. Band gap is important because it gives you the semiconductor-like properties. You can create an N-type and P-type material and control the conductivity that way. The mobility is important because that's how fast the electrons can move through your material. That determines how resistive or conductive a material is. And the features that we pointed out here, graphene has really high mobility in the tens of thousands. So that's one of the reasons why it's placed up here. Silicon is right about here, right in the middle of the map. About a mobility of 3,000, 4,000 or so centimeters squared per volt second. You get to some of these monolayer materials. These are, I think this was moly. So this was a popular two-dimensional material that has lower mobility but a large band gap. And I don't quite remember what this bilayer graphene and black phosphorus was, but these are some materials that were being tried out because of their mobility properties. Right. So the point of this slide is to show you that when a new material comes out, like one of the things that researchers often do is they try to compare it to the existing material set, and they're often plotted out on a two-dimensional map like that. All right, so conductivity in a semiconductor. I mentioned to you a semiconductor has electrons and holes. So we actually have to account for both when we're looking at the conductivity of the material. So this basic formula that we talked about earlier, it only takes into account a single charge carrier. So this is the charge density, as I mentioned earlier. This is coulombs per centimeter cubed. This is mobility here. And then this is the conductivity. And the units for conductivity is 1 over ohm centimeters. So in a semiconductor, there's two types of charge carriers. There's electrons and holes. And you can calculate the concentration of electrons and holes based on what we did in class last time. Each type of carrier has a certain mobility. So we denote the conductivity of electrons as mu n and the conductivity of holes as mu p. And to find the effective conductivity, we would add up the concentration, the contributions of each type of carrier. So the sigma is equal to the conductivity is equal to the conductivity due to electrons times the conductivity due to holes. And the formula to find the conductivity of electrons, you use this general formula up here. You multiply the mobility of the electrons multiplied by the charge density of electrons. And to find charge density, you take the concentration of electrons and multiply it by the fundamental constant Q, 1.6 times 10 to the negative 19. That's the charge for a single electron. So this is the conductivity due to electrons, mu n times q times n. And the second term here is the conductivity due to holes, mu p times q times p. And, if you just take the fact that q is the same here, you can take that q out, and you're looking at q times mu n times n plus mu p times p. In an n-type semiconductor, which of these terms is going to be more dominant? Mu n, correct. So in an n-type semiconductor, the n is very large. There's a lot of electrons in the conduction band, but the p is very small. There's very few holes in the valence band. So in the case of, this is the semiconductor mobility. Okay, got the constants there. So this term is dominant in an n-type semiconductor because this n is much larger than p. All right, so in an n-type semiconductor, you can actually ignore this next term, the second term. And so the sigma n is much greater than sigma p because n is much greater than p. And then in a p-type semiconductor, the second term is dominant. Okay, so it should be very straightforward to calculate the conductivity of a semiconductor. And mobility and the electron concentration, it results from doping. The more you dope it, the more conductive the semiconductor becomes. So a quick calculation, a quick demo of calculating conductivity. I guess it would be helpful to do this one together. So calculate the conductivity of silicon doped with 10 to the 17th per centimeter cubed of phosphorus. Compare it to the conductivity of intrinsic silicon. All right, so let's do that first part here, and then the resistance we'll do that if we get time. So I would like everyone to give this one a shot here. So 10 to the 17th, or we can just do it together. All right, so let's just do this together in the interest of time. So the conductivity is equal to sigma n plus sigma p, and we know that since this is an n, this is phosphorus, is column 5. So this mu p is going to be insignificant. So this is for doped semiconductor. All right, and so sigma is equal to q times mu n times n. So this is equal to 1.6 times 10 to the negative 19 multiplied by the mobility. So the mobility is what we need to look up on a chart. So the mobility at 10 to the 17th doping. So remember, this is on a log scale. So we look at this on a log scale. This 10 to the 17th meets right about here. And if we look across here, we'll find that it's roughly 1,000. We're just approximating here. So 1,000 centimeters squared per volt second. And then the electron concentration. What is the electron concentration? 10 to the 17th, right. 10 to the 17th per centimeter cube. Remember, 1 electron per phosphorus atom that's put into the lattice. All right, and maybe someone with the calculator can help me calculate the conductivity here. Thanks, David. While we do that, I'll set up the undoped problem. Sorry, what was that? 16 1 over ohm centimeter. Okay. Can someone confirm that?
I got 160.
160. Okay. I'm just going democratically. There's 2 people who said 160. So. Undoped material. So with the undoped material, we actually have to consider both Q times mu n times n plus mu p times p. Why we have to consider both is because n and p are the same, right? In an intrinsic material, undoped material. So this is going to become q times mu n times ni plus mu p times ni. The hole concentration and the electron concentration are the same. They're equal to each other in an undoped material. So q times ni times mu n plus mu p. All right. And I think just in the interest of time, we won't bother doing that calculation. The only thing I want to point out here, 1.5 times 10 to the 10 is the intrinsic carrier concentration for silicon. And these mu n's and mu p's, again, you have to look them up on the chart here. The mu n, remember this line here, this line just continues at the lower concentrations. The chart only shows as low as 10 to the 14th, but we want to find the concentration, or we want to find the mobility at 10 to the 10. The intrinsic carrier concentration, the doping there, the impurity level is 10 to the 10. So we want to go way back here on the map. So we can just use whatever the value happens to be here. And this map is, the way that this log plot goes is that this is 10 to the 2, this is 10 to the 3. This line here is 2 times 10 to the 2. This line here is 4 times 10 to the 2, and so on. That's just the way this log plot is set up. So it's a 2, 4, 6, 8, 10. So this looks like the whole mobility looks to be about 500 centimeters squared per volt second, and the electron mobility looks to be what? Close to 200. Does that sound about right? Yeah. And and we actually have these mobility constants right here. The electron mobility for silicon is 1500. So I was close. So this is about 1500. So the mu n is 1500 and the mu p is about 500. So you have to do that full calculation for the undoped material. Yeah.
I still got the value as 16.
Oh.
It's 10 power minus 19.
Oh, look, well, I have the solution here. Yeah, I forgot that I had the solution on the next slide.
It's 10 power minus 19. 10 power 90, so
Okay.
16.
All right, so I'm putting down the verdict, sorry. My slide says 16, so... Yeah, so here's a solution. Sorry, I didn't realize that I had the solution on the next slide. We don't need to find the whole mobility because it's going to be insignificant. The electron mobility is 1,000 centimeters squared per volt second. So Q is 1.6 times 10 to the negative 19. Mobility is roughly 1,000. N is 10 to the 17th, and you get 1 over ohm centimeters. If you calculate the resistance, it's just L over sigma times A. And for this resistor, you get a resistance of 6.25 ohms. All right. Just one thing to keep in mind when you're doing the resistance calculations, the mobility is given in units of 1 over ohm centimeters. So your length units must be centimeters. Your area units must be centimeters. All right. And the conductivity of undoped silicon you can calculate yourself and check it with some online reference. All right, so I want to talk about velocity saturation now. At high electric fields, there's a linear relationship between carrier velocity and the electric field. Actually, the linear relationship between carrier velocity and electric field actually no longer holds. Instead, the carrier velocity reaches a maximum velocity known as the saturation velocity. So let's look at what this is. So if you have the electric field on the x-axis and the carrier velocity on the y-axis, what you'd like to see is a line like this. So if you remember at the beginning of today's lecture, we said that the velocity of the electron v is equal to mu times e. So it's a linear function of the electric field. in our discussion section, we also said, like, if you double the electric field, you double the velocity. That's the type of linear behavior that we would expect. That's the ideal behavior of an electron. It's this linear curve here. And let me just something there. Just so no one's confused, if it's a linear relationship like that, just a proportional relationship, then we would want it to intersect the axis like that. Right? What actually happens is what's shown in the green line. So initially, at low electric fields, the velocity is proportional to the electric field, so it goes up. Good behavior here, but at high electric fields, the velocity starts to trail off, and then it saturates like this. This is called the saturation velocity up here. And the reason why it does that is thought to be due to the optical photon generation when the electrons have a large velocity. So this optical photon effect is sort of beyond the scope of this class, but it causes the electrons to basically hit a maximum velocity. They can't go any faster than that. So the mathematical equation for this green line here is shown here. It's mu e times 1 plus mu e over v sat. So the way you can think about this equation is that at very large electric fields, this second term becomes dominant, and you're left with it becomes dominant over this 1. So you're just left with mu e over v sat. So it becomes v sat. At low electric fields, this term becomes insignificant compared to the 1, and you're just left with mu e. You're just left with the denominator. So at low electric fields, it's linear, and at high electric fields, it saturates to v sat. All right, so this is what velocity saturation actually looks like in common semiconductors. You're going to see some interesting and weird stuff here. First of all, if you look at silicon and germanium, silicon is these two lines here you can see is pointed out by the arrows here. There's a solid line for the electrons. You can see the electron velocity increases, and then it saturates, flattens out. For holes, you can see also the hole drift velocity is slower than the electrons because the holes have a slower mobility, higher effective mass. So the holes are also going up, and they start to saturate up here. The saturation velocity for electrons and holes, 1 times 10 to the 7th for electrons, 0.6 times 10 to the 7th for holes. And but something interesting happens in these what's called these multi-valley materials. Germanium also follows this similar type trend, but multi-valley materials like gallium arsenide, we're going to talk about this E versus K diagram in the next lecture. So this multi-valley material thing will probably make more sense later. But these materials have multiple valleys in the conduction band when you look at the E versus K diagram. We'll talk about that next class. As a result of that, when electrons transfer between the different band minima, they have different effective mass, and that results in different mobilities. The net result is you get some really weird things that look like this, where like if you look at gallium arsenide here, the carrier drift velocity increases, and instead of tailing off, it peaks, and then it actually decreases. So that's that's a pretty strange behavior. It increases and it peaks around 10 to the 3rd, and then it decreases at higher electric fields. So that has to do with this electron transfer between the different band minima. That changes the effective mass of the electron. Effective mass reduces the mobility, and that's why you see a decrease in the velocity. This should be probably a fairly obvious question by now, but if you compare the saturation velocity of silicon and gallium arsenide, notice that gallium arsenide, the saturation velocity is higher than silicon, right? It has a much higher mobility here. I think we actually talked about this already. So gallium arsenide would be better for high-speed electronics just because it has higher mobility. All right, the last thing I want to cover in today's class is the energy band model of drift current. So with everything we do in this class, your understanding will be at the best it can possibly be if you understand all the phenomena in terms of the particle model and the energy band model, or the wave model. The energy band diagrams have to do with the wave-like behavior of electrons, and when we talk about the particle-like behavior of electrons, we think about it as like a particle object that's subject to Newtonian mechanics and that's just moving through the lattice. Notice that we've kind of done that. The particle model has to do more with like a physical model. Like you can try to picture small particles. You can picture the lattice, and you can picture things moving through the lattice. Okay, so you can also think about it as a physical model. Okay, I want you to have a physical picture of what's happening, phenomena that are happening, and I also want you to have the energy band picture of what's happening. The energy band model derives from Schrodinger's equations. It talks about the different energy states that an electron can have. All right, so this is an example. Drift current is it's one of the most fundamental transport mechanisms for electrons. And so I want you to understand it in the physical model and the energy band model. The physical model was the electrons are behaving as particles and they're just moving through the lattice. They're jumping from state to state. They collide. The collisions slow them down and so forth. Right? That's drift current in the physical model. And that's where we're looking at electrons as a particle. The energy band model of drift current is shown in this slide. And this is where we look at the energy band diagram when we think about electrons going to its most lowest energy state. Right? Electrons are happiest in their lowest energy state. As we do this, you're going to become more and more familiar with energy band diagrams, and you're going to have a set of rules in your head on how energy band diagrams work. And so one of the first rules that you can try to remember about energy band diagrams, well, you already have a few. You draw EC, EV, and then the position of EF tells you the doping level, right? So that's one thing you know already about energy band diagrams. The second thing is that at equilibrium, the Fermi level was flat. It was a horizontal line. Remember that? So that we looked at that a semiconductor in equilibrium. When you add a voltage to across the semiconductor, the Fermi level on the negative side is higher by convention. All right. So we place a voltage across an N-type semiconductor. The right side is negative voltage. The left side is positive voltage here. Whichever side has the positive potential has a lower EF. Whichever side has the negative potential has a higher EF. So placing a voltage across a material, it changes the respective Fermi levels on the two sides. All right? And here's a way you can think about it. Do you remember when you place a voltage, you're creating potential energy, right? Where is the potential energy higher? It's higher on the positive end, that's right, and it's lower on this end. But if you were to place an electron, where does the electron have the most potential energy?
Lower state.
Yeah, on the negative side, right? Remember, the way that you can think about potential energy is if I were to, if everyone can see my mouse here, if I were to take an electron and put it here and release it, that electron's going to accelerate, right? If I take an electron on this side and let it go, there's no potential energy. It's at the end. It's at the end of it. If you put it near another negative charge, then the negative charge will repel it and it'll accelerate away. So the electron has more potential energy on this side. It has less potential energy on this side. So that's sort of the philosophy of the energy band diagram. So the electron has high energy on the right side. It has lower energy on this side. So what's essentially happening is that the electron, these are all energy states, right? Everything above EC, there's a band of energy states. So there's a whole bunch of different energy states here. So the electron that initially starts off here just hops to lower and lower energy states as it's going across. So the electron hops into one energy state, it sees another energy state just to the left of it that's a little bit lower energy, and it keeps on hopping back and forth. The electron is trying to go to a lower energy state. It sees a lower energy state nearby, and it just jumps into it. All right, and the electrons are moving from right to left, so the effective current is going from left to right. We define current as a movement of positive charge, so the current is opposite the direction of the electron movement. So drift in a p-type semiconductor is similar. The holes go in the above direction, and the difference here is, it's similar. Like I've just drawn this. This is positive on the right. Whichever side is positive has a lower Fermi level, so the right side has a lower Fermi level. And one thing I think I forgot to mention is that the EC and EV, they also tilt. Because the spacing between EF and EV, remember that's determined by doping. So the space between EV and EF has to stay the same everywhere because it's doped the same everywhere. The spacing between EF and EC also has to stay the same because this is a uniformly doped material. So when EF tilts like this, EC and EV also have to tilt. And the way that you can think about this is that holes like to move up the slope. Just like electrons like to move down the slope, holes like to move up the slope. That's the rule of thumb that you can remember. What is actually happening here is that remember there's a whole bunch of states here, but all these states, remember these states are full. The hole represents, let's say this, you have a state here and that state is full, meaning there's an electron and another electron, two electrons like this. So if there's an empty state right next to it, what's going to happen is that the electron will actually go to the lower energy state, and that causes the hole to move in the opposite direction. So the holes moving up the slope is actually the electrons moving down the slope, and the holes end up just moving in the opposite direction. So again, the electron sees a lower energy state that happens to be empty. The electron moves in this direction, and the hole transfers in the opposite direction. So holes are moving to higher potentials, or what seems like higher energies in the energy band diagram, because the electrons are actually moving to lower energies. All right, so I think this is a good stopping point. So the discussion question here is, what is the conductivity of undoped silicon? We did that. We did that calculation, so we don't need to do it again here. So, okay, good. Well, we finished what we need to finish for today. Next class, we're going to talk about electron energy and momentum, and that will be the end of Module 3. So the discussion on electron energy and momentum should take about half the class on Monday, and then we'll get into probably Module 4 on Monday as well. Check out the homework questions. They've been posted online, and see you all on Monday.
I had a question. Go back a couple slides. I had a question.
Sure.